Okay, well, okay, it's time to start the session. Welcome to the workshop, and we have a very, an interesting program, a very full program, and Jacques would be chairing it.
Well, thank you. So, the first session, we have 3 talks. So the first one is by Guillaume Munch-Maccagnoni about resource polymorphism, a proposal for integrating first-class resources into ML. This is a remote talk, but you can see Guillaume here on the laptop. Okay, can start.
Thank you, Jacques. Hello, everyone, and good morning. I'm happy to see you because I have video feedback, so it's as if I was with you. This looks very nice. So the talk I want to present here is about something I've been working on and off for a while now, about how one could make ML a better systems programming language. So there was a proposal to add first-class resources into ML, heavily inspired by C++ and Rust. So first, a quick background on resource management in programming languages. So a resource, in the way I will understand it in this talk, are for instance, things with a cleanup operation, where you have to call for a file, for instance, some close operation to be able to release the resource at a certain point in the program. And well, the more you do systems programming or parallel programming and things like that, the more you're low level in your programming model, the more resources you have to deal with. And for instance, in multi-core OCaml, the notion of linear continuation or 5-bar is an example of a resource because things go bad if you even forget to dispose of it explicitly. So we also see that in various frameworks that people are introducing in multi-core OCaml with custom schedulers, they introduce various notions of resources, various mechanisms to deal with the resources. So it's an important topic for multi-core OCaml. And this work in particular was started from discussions with industrial users of OCaml who said that they actually had issues programming with resources correctly in OCaml. So this example shows that it can still go wrong if you don't pay attention to exceptions that can arise. So in real-world OCaml, you would be advised to add a try with like this to close the file in case of error. So you always have to be mindful of the possibility of an exception. My definition of a resource would be a value which is hard to copy or dispose of. So you have to do something explicit if you want to copy it or dispose of it, if even you can. So in languages without a GC, this would be memory, of course. But even with a GC, if you have large amounts of memory, you might want to treat it as a resource. Those are the low-level abstractions from your OS. Things that need to be cleaned up, like mutexes. Things for which aliasing is harmful. So when you want to control aliasing to, for instance, prevent data races. And in languages like Rust, we also see emerging abstractions appear. For instance, things for fault tolerance in Rust. And in programming languages in which you can program with resources, any data structure containing resources becomes a resource, etc. So memory management, usage of a value that respects a protocol. So if you want to ensure that the file is closed, that the network connection is open before communicating, etc. And so with all these constants, we see that correct resource management is an issue for correctness, efficiency, interoperability, and expressiveness. So just from this notion, I have a broad range of concerns to address. More abstractly, I want you to see resource management as techniques to reason about the state of the program. And how do we do this? How do we support this in the language is by supporting a notion of linear value. But be careful to state linearity as a safety property rather than as a liveness property. Something like, if I am at this point of the program, then I am sure that this or this function has executed. And I need to talk about modern C++, C++11, and Rust, which represent breakthrough for these questions and which are a direct source of inspiration for the proposal. It started with C++11, which introduces resources as first-class values. So it's a notion of resources assimilated to linear values that were a bit anticipated by Baker in the 1990s, but papers that were very rarely cited in the programming language community. And Rust is important because it extends to C++11 with better static type checking. And it showed that those concepts are also relevant for concurrent and parallel programming. The key concept of these languages is that of a destructor, which is a function that is called when a variable goes out of scope in a predictable manner, including when an exception is raised. In ML, you might have unwind protect combinators, but the concept of destructor goes further than that. It is a type-level abstraction, so you can have an algebra of types, you can have abstract types representing resources, and so on, that you can compose. And the big thing since C++11 is the notion of first-class resource, in the sense that with a runtime technique to manipulate resources, you can pass and return resources. You can put them in data types, in standard library containers, and so on. So you can actually program with resources as if they are first-class values. And it is a central concept because linearity and ownership in these languages are emergent phenomena of these types without destructors. For instance, in Rust, you've got borrowing, which follows from this concept, then uniqueness, so with linear borrows, the notion of external uniqueness via abstract data types, and so on. And so I take it as a starting point to investigate such concepts in the context of ML. So the starting point for my investigation was work with Guillaume Munch-Maccagnoni back in 2017, where we actually reconstructed the notion of type with destructor in models of linear logic, essentially. And this gave us an understanding of destructors through some Curry-Howard correspondence. So destructors, types with destructors are understood as objects in a slice category. I won't enter the details, but the main result is that the structure that arises from that is very similar to the linear logic bang. However, instead of adding a kind of copyable types to linear types, like bang in linear logic, it removes copyability So it adds a notion of ordered logic to intuitionistic logic. And this was a bit a new kind of object that we didn't know until now in the context of linear logic. So the starting point is we want a type-based abstraction. We want to attach a destructor to a type to create a new type. This will give rise to ordered data type in the sense that if I destroy A after B, it's not the same as destroying B after A. And so ordered logic is weaker than linear or affine logic, but if we just look at what the type system does, I am still as expressive because I can destroy by calling the destructor, or I can move. It's ordered because move is an effect, and so A tensor B is not isomorphic to B tensor A. This explains actually phenomena that you see in Rust, this ordered phenomena. For models of linear logic and linear logic applied to programming language semantics, it solves an open question of how do we combine linearity and control effects, such as exceptions. So we answered the question, are types in Rust linear or affine? They are linear for values. Values are linear. The types are ordered. And if we just look at the static type system, the types are affine. So it's a pretty clear answer to this question. I had several goals and methods to come up with a proposal to extend first-class resources. First, I don't have a working prototype. In my proposal, I propose ways to translate some pseudocode into actual OCaml code. I did not address the question of a type system, which is left as a challenge. For this, there is a lot of relevant literature. And I talked a lot about language abstractions and how it could be implemented and how it works at runtime. So we want to find some ML-like sweet spot. And I wanted something which is rooted in programming practice and experience. So my goal was not at all to take the semantic objects and put them in a programming language. I was really inspired by how can I make ML a better systems programming language. And I was also inspired by not just the move semantics in C++11, but how it came to be, because by making resources first class, there were a point in language design where it would enable gradual migration from old code to new code. And they were careful of having something which could really interact with all the rest of the language. That was a key design goal, so that you don't end up with some kind of dialect when you program with resources that interacts poorly with the language. So I took inspiration from C++11 on this point. And there's no point in making a proposal that works backwards compatibility. I won't say more about it. Basically, you want to add a new type. So you consider a type U, you add a destructor to it that gives you a new type T. And you want a type of borrows of these types. At runtime, you have a kind distinction. You need a distinction at runtime between types with destructors and types without destructors. So such a distinction of kinds is inspired by priority in linear logic. It's also very similar to the special traits of Rust, drop, copy. And so I will explain the new terms. For instance, if for a file, say from the standard library, I can create a new kind of resource that represents a file. And when I want to create a file, all this is looks really like ML. When I introduce the file keyword below, I am creating a file, and I return a resource, and so the consumer of this resource, so the caller, will be responsible for calling the destructor, which these destructor calls will be introduced by the compiler automatically. For instance, if you have some value x in a function name drop that you do not use, then this will immediately call the destructor. But it's also the case with fancy drop. If you raise an exception, it has to be dropped. If you consume open a file by calling open file, so you receive a file in variable x, then you can move it elsewhere by calling another function. This moves the resource. If you try to copy it, you expect to receive an error, because if you copy an own file, you no longer know when to call the destructor. And you want it to interact with data types. So you want data types that contain resources. So if I have a list of file names, for instance, I want to be able to map this list to a list of a name and an open file. And the result will be a resource, which is a list containing resources. And what could happen? You could open a list of files. One of these files do not exist, so you get an exception. You expect that you have created a certain number of resources until now, until you get this error, and they will all be cleaned up automatically as soon as you get the error. So it would be a bit verbose to implement the same thing by hand. So I need a notion of polymorphism to be able to mix. So I want my resources to interact well with the rest of the language, and I want to avoid a language which is too verbose, where you have to duplicate code and specialize it to many different situations. And for instance, if you want to implement the map function on lists, you want to do it once for resources and non-resources. So you would write something like that. So you have to think about, how do I compile functions that are polymorphic. So I won't say too much about it, but it is possible, since there is a finite number of kinds to consider at runtime, to monomorphize. So there will be two options per distinct type variables to compile. So there is a lot more to say about it, but I won't talk too much about implementation strategies. I don't talk about the typing. The notations are inspired by the brilliant work of Jesse Toff and Ricardo Pucella about having a practical type system for affine types. Since I am ordered but still affine at the level of typing, this is a valid source of inspirations in terms of type system. So I'd like to skip the notion of borrowing for lack of time. There is a notion of polymorphism of borrow, which is important. And I want to talk a bit about resource management, because one of my goals with this project is to mix different strategies for allocating memory. So in languages without a GC like C++ and Rust, they have different techniques to allocate memory. They use stack allocation and memcopy. So this is a different work than the present proposal. And they have unique pointers with ownership. They are tracking the ownership of memory cells so that they can free them promptly and not sooner than needed. And this is supposed to be as efficient as malloc and free. And they need to use various strategies like having reference counted pointers when they want to share data and so on. And reference counted pointers have many drawbacks. Most of you know about it. So one of the most important for ML is the lack of cycles, for instance. And so there are ways to improve reference counting by various methods, and you will have a talk later on that. And I wanted to talk about this paper, which highlighted that the difference between reference counting and garbage collection is a bit misleading, because we have actually a variety of techniques that are a bit in between RC and garbage collection. Reference counting, so we want to get rid of it. We prefer GC because it handles leaks. It can be nicer for latency and so on. But still, reference counting is good for timely resource destruction. So I understand languages that use reference counting for that. So the correct point of view to me is to see two possible directions. If you start from RC, either you improve it in certain ways and you get to some kind of GC. You can improve it in a different direction by preserving different qualities of reference counting, by pushing it towards ownership and destructors or on RIII. So in this diagram, OCaml will be far to the right. And later you have a talk on Perseus, and I put it just a bit to the right. So Perseus, they experiment with reference counting where they can reuse memory. So it's nice for experimenting about functional programming where you can reuse memory cells. And I put it a bit to the right because it is still not possible to reason about when your memory is collected, in the sense that if you had resources attached to values, say finalizers, like for GCs, you would not be able to predict when they run unless you know the algorithm. And my goal is to preserve this property, to be able to predict when the resource is collected, because I want to be able to handle other kinds of resources, and I want, if I have large amounts of memory, I want to be sure that it's not collected in the middle during a hot loop, for instance. And so I want a language where I have both RIII and GC. So there are advantages to GC. And on the other side, with RIII, we get a lot of different advantages. So I won't enter the details to have some time for questions. But mainly we avoid the drawbacks of reference counting by a static ownership discipline, which removes many issues such as cycles. So I have two works, two experiments presented at ML and OCaml workshops on on this. So one observation is that one drawback of area is that you need to have an ownership and borrowing discipline, and you need to traverse the whole structure on destruction. So you cannot benefit from a general hypothesis. So the claim is that since you are already paying the cost of that, then you most likely want to allocate all your resources, everybody of kind O that I showed in the previous section, you want to allocate them linearly, so that you can take advantage of linear allocation with reuse. So there are two experiments. One is box root. I work with Gabriel Scherer. When I explain how I can embed a garbage collected value into an own value. So it's the idea that you are going, if you create a root for a GC, you are creating a resource because you will need to unregister the resource. And so it's a bit like the smart pointers in Rust, where you make a resource out of some memory, and in this way you embed the garbage collected world into the resource world. The result of the experiment is that it can be done efficiently. It's interesting because you are mixing techniques from efficient allocators and techniques from efficient GCs when you implement that. And one of the conclusions is that the cost of introducing a root in this way is already paid for in a certain sense. It's not more costly than into allocating a memory cell with malloc. And in the other direction, we can embed the own world into the garbage collected world. So it's the converse direction. If I borrow something which is owned, I can pretend that it's allocated as a normal value because I have a uniform representation of values. And when I call a function meant to manipulate garbage collected values, it actually does not care how it has been allocated. So for this, there is an experiment at ML'22 where I showed that it does not cost anything to add a way to discriminate between people inside and outside the heap, inside the marking loop of OCaml. Actually, it made it run a bit faster, but negligibly so. And that was a bit of a surprising result. And with these two features, one can mix GC allocation and linear allocation with reuse. So there are challenges for typing. I won't enter the details. And here is a summary of the talk. And I will welcome your questions.
Okay, so are there questions? Yep.
Hi, Guillaume. This is me, Neil Krishnaswamy.
Hi, Neil.
So in C++, you don't just have move and drop constructors. You also have copy constructors. And I wondered if you know, like being able to implement your own contraction was something that you had considered or which you thought might be either useful or harmful.
Let's say definitely harmful because there is too much freedom in C++ in this respect, in my opinion. I'm not sure that we want something which is automatic, like a copy trait. And then if you wanted something like reference counted, this is perfectly valid, some kind of reference counted resource. but you would not want to make it a core trait of the language. As in, actually, I'm not saying anything new. This is what they do in Rust. Like the clone of RC is not at all implicit. So it's orthogonal to what I'm proposing.
Ron Minsky from Jane Street. I'm curious how you think this work relates to the work on mode and uniqueness mode and stuff that's currently happening at Jane Street, and whether that kind of fits into the kind of typing story that you might fit into, that you might want to have for this kind of resource management.
Oh, there is a lot to say about it. So I have to thank a lot Leo and Steven, because we had a lot of discussions about this proposal, and they've been doing like something like unboxing, which is orthogonal, but which I mentioned was still useful to so that this proposal pays off dividends. And the work on ownership has a different method, and one aspect of my proposal was that, or at least I was hoping, that by having something ambitious but with a large payoff, we would motivate working on a much more expressive notion of ownership and borrowing. Whereas what I have seen, so I have only seen the blog post on the locality thing and ownership and all that. But there are more like low-hanging fruits to reason about ownership. So it's a bit orthogonal in a sense, but I'm hoping that with our resource management proposal, we would be able to motivate and push it further towards something more expressive. Thank you.